Here we're going to look at an allylic carbanion. This is another 3-atom system. And it's similar to the carbocation in that we have a charge next to a double bond, but now we have a negative charge. And don't forget that that negative charge on the carbon means the carbon has a lone pair. So we can move lone pairs, we can move pi bonds. So the lone pair I put in blue, I'm going to make the pi bond red, and we're going to see how we can move this. Now, in this case, there's no positive charge. So there's no hole that wants electrons on the molecule. Instead, what we have is the lone pair that's kind of an excess of electrons. So once again, I'm going to draw in the hydrogens, just so we can make sure we don't violate any valency rules. And now what we're going to do is set our pencil down on the lone pair. And instead of having it set on this carbon, I'm going to push it over here and share it with the neighboring carbon. So we're taking that lone pair from the carbon, sharing it to the neighbor to form a pi bond. But what happens when we do that? We're putting pressure on this carbon. This carbon can't have 5 bonds. So if you're adding electrons to it, electrons have to move away from it. But we have this pi bond that I can move, and that pi bond goes on to this carbon on the right as a lone pair. So when we translate that into the structure, again, in black, I'm going to draw the sigma bonds. For the carbons, I'll draw in the hydrogens, which is not something you have to do every time, but while you're getting started, it helps. There's our sigma bond framework. We end up with a pi bond here, and we put a lone pair on this carbon. This carbon on the right now bears the -1 formal charge. So with lone pairs and pi bonds, they can't go far. So this lone pair is still part of this carbon. It's now just shared with its neighbor. This pi bond is still part of this carbon. Right now it's shared between the two, but it leaves the carbon in the middle and goes onto the carbon on the right as a new lone pair. So to write out basically what's going on here, this lone pair moves into the bond to form a pi bond. Then the pi bond moves on to the atom as a lone pair. And that's our basic allylic carbanion system. This is something you can have in a much larger molecule, but we can still narrow it down to this small 3-atom system. Let's look at something a little more complex, but it's the same basic thing. This structure right here. What we actually have are 2 different allylic systems. And we're dealing with non-carbon pi bonds, but that's okay. So we have the lone pair next to the CO pi bond, that's one system. We have the lone pair next to the nitrogen pi bond. That's a second system. But we can draw 2 different resonance structures with this. So if we want to draw the resonance structure using the pi bond on the right, move that lone pair in to form the double bond here. Then we'll push this pi bond onto the oxygen as a lone pair. Everything else stays the same. So I get a new pi bond here. The oxygen gets a new lone pair and the negative charge. Now you're going to get to the point where this is really all you need to draw. But for now, to make sure we're keeping track of everything, this oxygen started out with 2 lone pairs. When we did this resonance movement, it received a 3rd lone pair. Now, if you move this negative charge through the other 3 atom system, the lone pair goes here to form the pi bond. This pi bond goes up onto the nitrogen. I'll go ahead and draw in. The nitrogen currently has 1 lone pair. So double bond O. Now we have the pi bond here. And H, we have the original lone pair and the new lone pair. If you calculate the formal charge of this nitrogen, it's -1. So in this particular case, here, these electrons in this structure are actually delocalized over 1, 2, 3, 4, 5 atoms. And what we'll eventually learn is that this is really kind of a good thing, because delocalization is stabilization. And we want molecules to be as stable and happy as possible. So if these electrons are delocalized, they're in kind of a happier environment. In addition to saying this is delocalized over 5 atoms, you would say that this molecule has 3 resonance structures. Okay, but I do want to again hit home the point that neither of these 3 structures really exist. There's one true structure that is a hybrid of the 3.